All right, so now let's look at some of the ways that we can characterize or measure this fracture toughness, K1C, but also the strength of ceramics. All right, so one of the ways that we can get K1C is through a bend test, and we're going to talk more about this in a little bit as well, but you'll probably remember bend testing from the lab, where we take a material and put it under a mixed state, stress state, where it's being bent either by 3-point or 4-point, and this causes tension and compression depending on the location. And this is one way that we can test ceramics. So we can do a modification of that to get K1C. So K1C is all about a material's response to a flaw. And so what we do with these K1C tests is we actually pre-fabricate a crack or defect into the material. And so in this case, we take a bend sample, a bar, and we actually put a crack halfway through the material. So there's a couple different designs here. There's kind of this design where we just basically put a notch in here that takes up half the volume. Here we put more of a chevron design in the notch. So there's different geometries, but the same idea is we predetermine a crack, and then we bend the material and look at the material's response to that. So I'm not too worried about you knowing these equations, just to know that we can put a crack into this material and bend it, and then determine the K1C from that, from the bend test, from the failure or the stress at which it fails, and then also the dimensions of the material. So that's one way. Another way that we can kind of approximate it, and there are some limitations to this method, but we can use microhardness testing. And so very similar to hardness testing, but we're doing it on a much smaller scale. And so the common way to do this is with a Vickers microhardness testing machine. And so the idea is we have a very controlled indentation piece with the Vickers test. And we apply a very small amount of force to that indenter into the surface of a very polished sample of the material. And so when that force is applied, it creates an indentation, right? And so this area here is the indentation in the material. So just like a normal hardness test, we're going to have an indentation. So it's resistance to plastic deformation, right? But because these are very brittle materials, they're also going to crack. And so beyond that indentation, so if we look at the top view here, then this is the indentation, this sort of diamond shape, but it also has cracks sort of radiating off the corners. And so that happens in both of these sort of geometries that we see here. And so with the measurement of the hardness, the indentation size, and also the crack length, and so here we're calling it 2C from length to length, so from here to here, we can get a measure of the K1C. So I will say that this is a very quick way that you could get this measurement without having to make sort of specially designed test bars, but there are some limitations. That I've seen some papers out there saying that the credibility of these numbers isn't great. All right, so at this point, we've talked about all of these different types of response to cracks, and we've been talking about it really in one type of stress state, where we have a crack on the surface or interior of a material, and then we pull that material in tension, right? But we know there's different stress states, and we know there's different responses. So we know that in tension, cracks tend to be unstable, right? And that's why they fail. So in compression, so if we do the opposite, the cracks in compression tend to be more stable, and so they tend to propagate, but they do it more stably, and they tend to actually line up and kind of line up together, and you'll see these kind of matching up and forming much larger cracks, but they do it more stably in this case. And so the failure stress for material in compression is therefore then not dependent on the smallest or the largest crack size, It's instead dependent on the average size. So it's less affected by that material. And so that's why then we have failure strengths that are higher in compression. So it's much safer to use them as well because of the stable link up that we see here. So this equation, again, not super critical. The main takeaways here are that we're dealing with an average crack size. And then again, this Z is just a constant. And so it's roughly, you can just approximate it as 15, but it just gives you a rough measure of the failure strength for this material. And so just a quick note on the terminology here. So when these link up and form these cracks that are much larger, we call that the crush zone. So that's the only sort of additional thing that I want you to sort of get from that. All right. So like I mentioned, what we've been talking about so far is basically tension, right? So, and that's basically this first mode. And so you'll notice that in this case, we have a crack, right, or a flaw, and then we're basically trying to open it up. And so we put it under tension, right, so that there's a stress concentration at the crack tip. So this is what we call mode 1. And so when we saw K1C or K1, that was talking about the mode. And so that meant that it was in this tension. So like I mentioned, there's other types of modes as well. You could have it in this sort of shear, where we have a crack and you basically try to shear it open. That's mode 2. Or where you try to put it in torsion, and this is mode 3. So there's different types of mode, but we typically, for our sort of schematics and so forth, just try to show mode 1. All right, so I've mentioned that plastic deformation is fairly rare in that it can modify that expression of K1C if it does happen. But again, keep in mind, it is in other classes we've talked about how dislocation motion is less common in ceramics because of the ionic or covalent bonding as opposed to metallic. But that dislocation motion is also thermally activated. And so it's very hard to move dislocations at room temperature in ceramics. But if you give it enough energy, then that can be the case. And so this is just kind of showing that we have a dislocation, nothing really happens to it. But here we have a dislocation, and then we do actually have some plasticity around the crack tip. And so this is because, if you think about it, ceramics are very brittle, but they're also high temperature materials. And so when we're using them in those high temperature applications, we also have to consider that we have more thermal energy. And therefore, in those situations, dislocation motion may be more of an issue than at room temperature. So it all really depends on the conditions under which you have these materials. If you have them at high temperature, we often have to consider dislocations in more detail. All right, so we've looked at some ways we can measure this fracture toughness. And to get strength, ceramics are really difficult to test in tension. So if we want to try to do the standard sort of tensile test, it's really rather difficult. And some of the reasons that is, that shape, that dog bone shape that you're accustomed to seeing is very difficult to machine in ceramics because flaws are always going to be introduced on the surface or in interior. If you try to make screw threads, that's also going to be very difficult, and they tend to break in the grips. We also have issues with the actual testing. So ceramics don't exhibit much strain because they're very brittle. And so alignment is very critical. If there's any sort of misalignment, that affects your test. It's no longer in uniaxial tensile. And so alignment would become absolutely paramount. Misalignment would basically introduce bending. And then also our brittle materials are inherently weaker in tension than they are in other forms of other stress states. And so they're weaker than they would be used in their true applications. And so these are all reasons why we don't test in tension for the most part for ceramics. And so to get around these and to test more easily, for the most part, we use bend testing. And so this can be a number of different ways. Here I'm showing you 4-point bend because we have 4 contact points, but you can also do 3 contact points, 3-point bend, where we have 2 on the bottom and then just 1 right in the middle. But this is a way in which we can apply a bending moment to the material. This is a mixed stress state where we have compression and tension. Excuse me. So it's not pure tension, pure compression. It's a mixture. It's a bending moment. But we're able to calculate a stress at which the material fractures. And so this is one way we can sort of measure the strength in bending of these materials. And so if I have a rectangular cross-section with W and B as the dimensions of the cross-section, then I can calculate what's known as the modulus of rupture, or MOR, by this equation. So the S1, S2 are the spans. So S1 is the bottom span, the larger. S2 is the top span, which is the smaller. P is the load. And then again, B and W are the dimensions. So we can do the same thing for a circular rod with a diameter D and everything else the same, S2, S1, all that. And we can write it as such here. So this should look familiar to those in the lab. Very similar expression for the flexure strength. Flexure strength and modulus of rupture are more or less the same thing. And so that allows us to calculate the strength in this type of stress state. And so this is an alternative to tensile or compression testing. All right, so now I want you to sort of get familiar with this equation, these equations, and the calculation of this modulus of rupture, which is just, again, a strength. And so let's say that I have a circular or square cross-section. Either way, the diameter or the side of the length is 5 millimeters. And we put it in this 4-point arrangement, so the arrangements we see here. And let's say that both of them fail at a force of 1 kilonewton. And our spans are the same. So we have 4 and 2 centimeter spans. So see if you can calculate the modulus of rupture for both of those dimensions and compare them. And we'll come back and take a look at those values. Excuse me. All right, let's go ahead and take a look at these. So I've re-put the equations here. Again, the dimensions here for the rectangular, I'm assuming that both B and W are 5 millimeters. So I'm plugging that in to the equation here. So basically, since that's all the same, it ends up being cubed. Our span, in this case, we have 1 minus 2. So it's basically 4 minus 2 centimeters, so 2 centimeters or 20 millimeters. And then we have 100 newtons, so kilonewtons, 1 kilonewton, so 1,000 newtons. And so putting all that in, you'll notice here that I have my units are in millimeters, Newton per millimeter squared. So the reason I use these units and not others is because I know that if I calculate Newton millimeter squared, it's the same as megapascals. So as a check, you can do this yourself. Calculate it in Newton meter squared and compare that, convert it over to megapascal, and see that those two are the same. So for the rectangular, I get 240 megapascals. And if I do the same calculation, assuming the diameter of 5 millimeters, for everything else the same, I get 407 megapascal. So we don't expect these two numbers to be the same because the dimensions are the same, but we have a square and a rectangle, or a square and a circular, and so the areas are going to be different. So that's definitely going to affect the answer that we have here. But this is, again, just to start thinking about the modulus of rupture calculation that we have here, and what that means for this bending strength equation that we look at.